A reminder that there's a homework due on February 5th, and another announcement on Thursday. We don't have I won't be here on Thursday, but the topic that we were going to cover on Thursday, most of you have seen it, and it's on the least squares fit to tie. We saw it last, but I recorded the lecture and it's posted as a video now. If you want to look, for those of you who haven't seen it, you can look at it. So make sure to look at it on Thursday, as if it was a class on Thursday. Right? I just won't be there, but any questions that you might have, you feel free to ask. And for most of you, it's just a repetition of what you've already seen about the least squares fit to tie. So you could look at it if you want, but it's essentially what we've covered before. And this is so that you know what to do with the data when we go out on the field and collect our data, so you know how to analyze the data. So we have established a framework, a dynamical framework under which we can study partially mixed estuaries, and that dynamical framework consists of in the along estuary direction, we have the pressure gradient being balanced by friction. So that produces what kind of circulation? What kind of flow? A two-layer circulation, near surface outflow, near bottom inflow. And across the estuary, we have a geostrophic balance, the lateral pressure gradient being balanced by Coriolis, in such a way that this implies that there are no cross-channel flows, no flows going across the estuary. This dynamical framework that we have established. That's the implication. So what do you think can alter those assumptions? So at zero order, this is probably a reasonable framework. But then in reality, you're going to have some factors and some mechanisms that will alter this framework, that will make this framework invalid. What do you think those mechanisms are? What would cause the pressure gradient balanced by friction to be violated or to be modified? Wind forcing is one, yes. What else? So in general, instead of wind forcing, in general, atmospheric forcing, because you have barometric pressure changes and wind forcing. What else can modify that system, that dynamical framework? For those of you who printed the notes, you know. But just intuitively, can you imagine what can alter this two-layer circulation along the estuary and the geostrophic balance across? The wind is one, the tides might be another one, right? The amount of river discharge will modify the density-driven circulation. What else? Let's see. We have tides, we have atmospheric forcing, we have river discharge. The bathymetry and the morphology will modify that framework, as we will understand throughout the following lecture. So I want you to keep this in mind, that what we're going to be dealing with in the next maybe 5 or 6 lectures or sessions that we meet, or 7. We're going to spend a good amount of time looking at how all these factors modify the framework that we have established. Okay, so let's get ahead a little bit and think or guess, how do you imagine the tides will modify this framework? What other dynamical implications will tides add to this framework? Can you imagine? Will the tides add advective accelerations or nonlinearities? Right. They will, right? So the along estuary and maybe the cross estuary momentum balance should include advective accelerations with the influence of tides. We'll see how later on. But that's just getting ahead so that you can imagine where we're going. And also the tidal forcing will cause advective accelerations maybe in the across estuary direction. If there are curvature effects, you will have some centrifugal accelerations that will have to be included in the along estuary direction. So that's where we're going. And as we go through those explanations, hopefully you can put them in the context of this framework that we have established. Before we see how tides modify the estuarine circulation, we're going to open a parenthesis of 2 or 3 classes to talk about tides. First, we're going to do a review of tides, and then we're going to come back to the topic of the class and see how tides modify the estuarine circulation, the dynamical framework that we have established. So today, we're going to dedicate it mostly to talk about tides. So, do you remember what tides are? In your own words, without looking at the notes that you've already printed. In your words, what are tides?
The rise of the sea level because of the gravitation force of the moon and the sun.
Okay. So you told me what tides are and what causes them. But is that that's fine. What tides are is fine, but is that a complete explanation? The gravitational forces do gravitational forces are the only forces that produce tide? No? What else?
Rotation of the Earth.
The rotation of the Earth modifies the tide, maybe, but it doesn't produce the
wind
tide.
forces.
Well, that can modify tides too, but they don't produce tide. Well, in the strict sense of the word, they do produce tides. But say that
Pressure differences.
that's analogous to wind. But say talking about the astronomical effects. Let's think about astronomical effects. Are tides all exclusively produced by the gravitational pull of the moon and the sun?
Yes.
No? What else?
The other planets. I don't know.
Well, yeah, but let's assume we can eliminate the effects of the other planets. There's something that is very important that we tend to forget, and I want you to remember all the time that it's the centrifugal acceleration of the Earth in the planetary system. Because it's not only the gravitational pull, but also the fact that the Earth is accelerating away from the planet, or trying to accelerate. So it's the Earth is in balance, right? The gravitational pull. If there was no other force, the gravitational pull would make us collide against other planets. But there's the gravitational pull that keeps things in balance. So actually, the balance of those two, the gravitational pull and the centrifugal acceleration, that's what causes tide. And we can define tides as a generic term to define the alternating rise and fall in sea level with respect to land. And this is very important. It's produced by the balance between the gravitational force, mainly of the moon and the sun, and the centrifugal acceleration. How is that the centrifugal acceleration? Well, we'll see in a minute. But tide also occurs in large lakes, and not so large. In Lake Apopka, we can see a tide of around 5 centimeter range, as we have recorded in instruments recently. You know where Lake Apopka is? Near Orlando? Any? So how large would you say Lake Apopka is? It's maybe like 20 kilometers long and maybe 15 kilometers wide or something like that. So that gives you an idea where you can see tides. You can see tides in the atmosphere also. If you have good enough measurements of atmospheric pressure, you'll see that it alternates with the tide. Very small. And in the lithosphere also, the solid crust of the Earth, you can see tides. So just to remind us, the main source of tide generating force comes from gravity, from the law of gravitation of Newton, in which the force of the gravitational pull between two bodies of mass, lowercase m and capital M, is the force is proportional to the mass of both, and inversely proportional to the distance, capital R, between the two, the square of the distance. And the proportionality constant is the gravitational constant. That's 6.67 times 10 to the minus 11 Newton per square meter per square kilogram. So this is the crux of the matter. So we have the Earth and the Moon, essentially. So the centrifugal force is trying to pull the Earth away from the Moon. And for practical purposes, we will assume that the centrifugal force is the same everywhere on the Earth. The centrifugal force is trying to pull the Earth away from the Moon. In reality, it isn't, but for practical purposes, we can assume that that's the case. And then we have that the gravitational force exerted by the Moon on the Earth is depicted by these fuchsia arrows. And you can see that it's different depending on what side of the Earth we're on. If we're facing the Moon, the gravitational pull is greater than if we're away from the Moon. And why is that?
Because it's inversely proportional to distance.
That's right, to the square of the distance, right? So that's why it's lower. The farther away we get from the Moon, the weaker the gravitational force. So you can see that there's an imbalance between the yellow arrows and the fuchsia arrows. And so that's the imbalance is depicted by the light blue arrows. So that's the tide generating force, which is the difference between centrifugal and gravitational acceleration. So you see it's not only the gravitational pull, but also the centrifugal acceleration. And that creates the equilibrium tide. That's what's called the equilibrium tide, or theoretical tide on Earth. So you can see that at any given time there are too high and too low tidal levels on Earth, according to the equilibrium tide. So that's why we have two highs and two lows, or we should have two highs and two lows everywhere on Earth with respect to tides. We're talking about tides. So you have, at this point, you have one high, and 12 hours later, when you're facing away from the Moon, you will have another high, or approximately 12 hours. So again, I want to underscore that that's the equilibrium tide. So this is a theoretical tide. In practice, what happens? Or in reality, what happens? This theoretical tide gets modified by the geometry of continents, by the bathymetry, and then you have all sort of distortion. And that's what we'll see in a minute. And also by the fact that the center of mass of the Earth-Moon system, that is the center of mass in which the Earth and Moon rotate and translate in the universe, or in the solar system if you want, the center of mass is 1,700 kilometers from the Earth's surface, in the interior of the Earth. And that's because the Earth is 81 times heavier than the Moon. So that will modify this equilibrium tide concept too. Now, how strong do you think is the tide generating force? We said up here, if I go back, we say that the tide generating force is the difference between the centrifugal and the gravitational acceleration. But if you were to say the tide generating force is proportional to what? The gravitational pull is proportional to the mass of the two bodies and inversely proportional to the distance, the square of the distance. How about the tide generating force? The tide generating force is the difference between the gravitational pull and the centrifugal acceleration. So it's not that straightforward. It actually is proportional to the cube of the distance. So the tide generating, as we will see in a minute, so the tide generating force is much more sensitive to the distance between the two bodies than simply the gravitational pull. So remember, the tide generating force is the difference between the gravitational force and the centrifugal force. So the gravitational force at point A there on the diagram is given by the law of gravitation, and the distance between the center of the Moon and the point A on the Earth is given by the distance P minus S, where P is the distance between the center of the Moon and the center of the Earth. So effectively the gravitational force is the distance over which the gravitational force acts is P minus S. So that's it. And then the centrifugal force at A is given by that, but with a is given by that expression. So the imbalance, which is the type generating force, is the difference between the two. And this is not a straightforward difference to make because of the denominators are different, but if you go ahead and do it, it's like and taking into account that the distance t between the center of the two is 60 times the radius of the Earth. S is approximately the radius of the Earth. Then, again, you expand it in a series. I think it's called a Maclaurin series. You have to use some relatively fancy mathematical tool to arrive at this result. That the type generating force is proportional to the mass between the two, the radius of the Earth, and inversely proportional to the cube of the distance between the two. So that is, you have to distinguish between this type generating force and the gravitational pull. So you can see here quantitatively how the tides are not only produced by the gravitational pull, but by the tide generating force, which is greater than the gravitational pull. So the tide generating forces at each one would be the same, but with opposite sign. And this is an important cocktail party fact that you might impress your friends when you go to a party. Maybe you don't go to cocktail parties yet, but you go to parties, to beer parties. But every now and then you might go to a cocktail party, and you might be faced with a senator or a representative or even the president, and you could ask them. Actually, maybe you saw it already, but do you know how much larger the tide generating, which is larger, the tide generating force from the moon or from the sun?
From the sun.
From the sun? Moon.
Yes.
From the moon? Why?
No, from the sun. I would say from the sun.
You said from the sun? Who votes for the sun? Which is greater, the tide generating force from the sun or from the moon? From the moon?
Yeah,
everybody saw that. Yeah. Now he changed his mind. Why is the moon more important in generating tides than the sun?
Because it is closer to the Earth.
Because of the distance, right? You said that the tide generating force goes as the inverse of the cube of the distance, and it's proportional to the mass. So the sun is very massive, much more massive than the moon. Sorry, but the moon is much closer. So how much stronger is the tide generating force of the moon relative to the sun? Well, you saw it, right? So that's a silly question. It's almost twice as large. The moon, the tide generating force from the moon is almost twice as large. And that's because, if you remember these numbers, you can impress anybody. Because the mass of the sun is 2 times 10 to the 27 tons, while the mass of the moon is 2.3 times 10 to the 9 tons. So how many orders of magnitude? 8 orders of magnitude. Almost 8 orders of magnitude. Larger, heavier the sun than the moon. Almost 8 times. But the sun is 390 times farther away from the Earth than the moon is. So the relative tide generating force is the ratio of the two masses divided by the relative distance between the two cube. So you do that, and that comes up to be 0.46. So notice that we're comparing here the mass of the sun versus the moon. So that's why the tide generating force of the sun relative to the moon is 0.46 times. So almost 0.5. So again, the moon is twice more effective than the sun in producing tide. So that's a cocktail party fact. And actually, that's a nice qualifying exam question too.
Yeah, how they calculate the weight of the sun and
it's indirectly. I guess I don't know how they know the density. Does anybody know how they know the density of the sun?
I'm guessing by X-rays.
Huh?
No, but the gas is
Guessing by doing the gamma rays or
Yeah,
Some satellite.
I don't know, but they're indirect methods. And for the moon, I suppose that they use indirect methods, but they've been able to prove it now. They've been able to grab samples from the moon. But yeah, I don't know. It's indirect method, and also by assuming what the moon is like inside, what material. Okay. So we've discussed this, what alters the range and phase of tides produced by the equilibrium theory. You see that there are non-astronomical factors like the coastline configuration, the bathymetry, like you said, the atmospheric forcing, like wind and barometric pressure. And hydrography. Why did I write hydrography there? How can a hydrography modify tide? Fresh water, right? So how can fresh water modify tide? Fresh water is lighter or heavier than ocean water?
Lighter.
It's lighter. So whenever you have gradients of density or hydrography, you're going to have some gradient. They might not alter the tide that much, but if the tidal range is small, they might. So sometimes they might. And actually, they do affect sea level. I don't know if you've observed, unfortunately we don't live on the coast here, but if you've lived on the coast at any point in your life and you've observed how high the water gets during summer versus the winter, you could see that in general during winter sea levels are lower than during the summer. And why is that? How about the temperature of the ocean itself?
Because of the density.
Yes. The thermal expansion, because of thermal expansion in the summer. In the summer, when the water is warmer, it occupies more volume than in the winter when, like you said, it's more compact. This in the ocean, without any land influence. So this is very nicely observed in the mid-Atlantic region. That you see the low tides drying out huge expanses of coastline in the winter, but not in the summer. So again, hydrography could alter the tides over long periods, and global climate change might be one also. So these non-astronomical factors may alter the speed of the tide, that is how fast they can propagate, because the tide propagates with what speed? Yeah, square root of GH. Yeah, I'm glad that somebody said it this morning. And the tides could also produce resonance effects with a certain coastline configuration, which is similar to seismic, and they can cause storm surges. The atmospheric forces can cause storm surges and inundation, as you know. So let's look at that a little more. So in the open ocean, the tidally induced variations of sea level are just a few centimeters. If you can measure the tide in the open ocean, you'll see that it's just a few centimeters. But when the tidal wave moves to the continental shelf and into confining channels, the variations become larger. All right. So keep in mind that the tidal waves travel, we said already, as shallow, long waves. How so? How so? Why do we say that the tidal waves travel at square root of GH? What does that imply? It implies that they are long or short waves? Long waves. So if they're long waves, what is the requirement for a long wave? How do you distinguish a long wave from a short wave or an intermediate wave?
Large period.
How about the ratio of depth versus wavelength? What is that? Like 1/20, right? Yeah. The ratio of depth over wavelength has to be lower than 1/20 for it to be a shallow water wave. So how do we know if that's the case? H over L, H over lambda, depth over wavelength. What's the depth over which tidal waves propagate typically? What's the mean depth of the ocean? 4,000 meters. And what's the wavelength of this wave? Any idea? If I tell you 100 kilometers, maybe, but in the open ocean, the typical wavelengths are 4,500 kilometers. So that's a very long wave, if you can imagine that, 4,500 kilometers. That's a semi-diurnal wave traveling in 1,000 meters of water. Okay, so that, and the ratio of depth versus wavelength is 1 over 4,500. So that's much smaller than 1 over 20. So that's definitely a shallow water wave. So because it's a shallow water wave, the phase speed is, as you said in your morning prayer, square root of T8. So that's a shallow water wave. That's how fast it is. And really, the tide that you observe at any particular point, let's say Cedar Key or St. Augustine or Jacksonville, is a superposition of several harmonics. You can decompose the tide into a decomposition of several harmonics or constituent, also called. And the main constituents in general in the tides on the Earth are those 5. So it's useful to put these periods, these numbers, in your hard drive. It's useful because if you deal with tides, you use them frequently. So for the semi-diurnal principal lunar, which is the most dominant in most parts of the Earth, not so in the Gulf of Mexico that we study up here, in Panama City, for example, as we'll see later. But in most parts of the world, that's a dominant tidal constituent. And that has a period of 12.42 hours. Then we have the principal solar semi-diurnal, which has a period of exactly 12 hours. So it has to do with the sun, half of a day, half of a solar day. And then the larger lunar elliptic semi-diurnal, because of the elliptic orbit of the moon, has a period of 12.66 hours. And then the lunisolar diurnal has a period of almost exactly 24 hours, 23.93, and the lunar diurnal, 25.82, which is close to 1 lunar day, 25.82 hours. Now notice that in most cases, most people will tell you that there are only 4 main tidal constituents, which are the M2, S2, K1, and O1. I include the N2 because in much of the eastern U.S., that's more important, the N2, with a period of 12.66 hours, is more important than the S2. And we'll see in a minute what that creates. Okay. So again, that we can represent tide eta, sea level, as a superposition of several constituents. So A is the amplitude. This is the amplitude of the constituent that we're talking about. The frequency of M2. So what would be the frequency here? Sigma would be equal to 2 pi over 12.42. And with a given phase, and then we have the amplitude of the diurnal, semi-diurnal lunar. So here sigma would be 2 pi over 12, etc. So you can represent the tide as the sum of all these harmonics and reproduce a tidal signal with this relatively simple representation. How do you get? What is it that you need to know here to represent eta for a given spot? If somebody told you, I want you to tell me the tide, the harmonic, give me a representation harmonic of the tide in a given, in St. Augustine, for example. What will you have to do? Determine the amplitudes, you said? Determine the amplitudes of each constituent. What else? And the phases. So these are the ones that we don't know, the amplitude and the phase. We know everything else. We know the frequencies that we're looking for. But what does this time represent? The time of measurement or any arbitrary time. So what do you need to do then to determine the amplitude and phase? So in practice, what do you need to do? Disperse speed? Huh?
Measure velocity.
Velocities? Okay, it could be velocities, but we're talking here about sea level. Measure the sea level. So will you go and measure sea level? How do you measure sea level? With a pressure sensor or a tide gauge? So you go out to St. Augustine and deploy an instrument and record sea level. How often would you record? Every 12 hours only? One measurement every 12 hours?
Every 6 minutes.
Every 6 minutes? Okay. That's good. That's how NOAA does it. That's how the National Oceanic and Atmospheric Administration does it. Every 6 minutes. But every hour would suffice maybe, but every 6 minutes is good. And then over what period? More than a day? Yeah. More than a week? Yeah.
For a month.
For a month? Yeah, for a month. At least a lunar cycle that is 29 days. So that will allow you to distinguish among all those constituents. All right? So now we can use what's called the form factor, which is the ratio of the diurnal to the semi-diurnal constituents, the amplitude of those constituents, to define what kind of tide you have in a particular place. So to characterize the tides, you use that form factor. So when the form factor lies between 0.25 and 1.25, you say that the tide is mixed with a mainly semi-diurnal domination. Then when the form factor is between 1.25 and 3, the tide is mixed with a diurnal, predominantly diurnal. Then when the form factor is greater than 3, the tide is diurnal. And when the form factor is lower than 0.25, the tide is, yes, you guessed it, semi-diurnal. So here are some examples of what they look like. Yes?
When you say this K1, O1, what are you talking about? Like the amplitude?
The amplitude, yeah, the amplitude of the constituent. We'll see a couple of examples a little later. So you can see here that in a location in England, the form factor is 0.1, which means that the tide is semi-diurnal. Can you see the semi-diurnal character of the tide there from that record? Sort of? How can you tell that it is semi-diurnal? You have 5 days here. So how many peaks should you have? You should have 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And they're very similar consecutively. They vary very slowly. They change very slowly, but the consecutive peaks are similar. So that means that it is a semi-diurnal tide. Then in San Francisco, California, on the west coast of the U.S., the form factor is 0.9, which means that it's a mixed tide with a semi-diurnal dominance. So you can see that it's mixed because you have a strong diurnal signal and a strong semi-diurnal signal. Although there's a large asymmetry between consecutive high tides. You see high tide here, and the following high tide is not that high. So there's a strong asymmetry. So this is a semi-diurnal tide with a mixed tide with a semi-diurnal dominant. Then in the place in the capital of Philippines, you have the form factor of 2.15, which means that that's a semi-diurnal, a mixed tide with diurnal dominant. And you can see that it's mostly diurnal. These modifications to the sinusoid shape are produced by the semi-diurnal influences. But you can see that they're very minor. The main thing that you see is a diurnal oscillation. During neap tides, you see some semi-diurnal influence. That's when the diurnal influence cancels out, and that's why the semi-diurnal appears. And then finally, you have a purely diurnal signal with a form factor of 20 in Vietnam, and that's diurnal all the time, as you can see. So something very important is that the superposition of constituents generates a modulation. Notice this modulation, the long-term modulation that you. So in this case of the diurnal, the purely diurnal, what do you think causes that modulation? Why do we have these nip tides and these spring tides? An easier question is if we go back to the semi-diurnal. What causes these nip tides and these spring tides? What happens to the sun and the moon when we have these conditions?
90 degrees in the middle. They are 90 degrees perpendicular to each other.
That's right. They're normally distributed. So they form a 90-degree angle. The sun, the earth, and the moon. So what that means is that the tide generating force of the sun is canceling out the tide generating force of the moon. And you have small tidal ranges. So that's nip tide. And in contrast, during spring tide, the earth, sun, and moon are aligned. So the tide generating force are additive. Now mathematically you can see this if you add the two semi-diurnal constituents from the moon and the sun, the M2 and the S plus the S2. If you add them in a long time series, you will get that modulation, a fortnightly modulation, every 15 days approximately. You will get a high, a large range or a small range. We know that, right? How can you explain then the diurnal? This diurnal modulation, which is also a fortnightly modulation. Is it the same thing? The K1 has some solar influence. Remember, it's close to 24 hours, and the O1 is close to the lunar day. So the O1 has more of a lunar influence. So it's the same, but for the diurnal constituent. And you can add two harmonics, one with a O1 frequency and one with a K1 frequency. If you add them over 30 days, you'll get a modulation that looks something like that. So this is a very important aspect to underscore, because this applies both for sea level and velocity. So in the case of the N2, when the N2, remember I mentioned that the N2 is more important than the S2 in the mid-Atlantic bight. So what that does is that the consecutive spring tides will be asymmetric. Within 1 month, you will only get one good spring tide, and the other spring tide will be like this. Maybe I have an example here. But we'll look at an example in Ponce de León later on about this. I'll come back. But here we have the subtidal modulation by two tidal constituents. So here we have the red, the blue one. The blue one is the 12-hour period, the S2, and the orange one is the M2. So if you add those two, the orange and blue, orange, blue, then you get the red. You get the red, which is the modulation. And maybe you won't see it on the screen here, but you can see it on this screen. And I'm going to have to go back and forth. You'll be able to see it on this here, the modulation. So for those who can't see it, you can go to the lecture notes and play the animation from the PowerPoint presentation. So if you can plot the lens through without moving the very good. So the modulation is given by this bar, by this red bar. So you can see the orange and blue are getting out of phase there. They're completely out of phase right there. So that was the minimum amplitude of the bar. that is of the red, which is the result. And now the orange and blue are getting in phase. They're getting in phase there, so that's the maximum amplitude of the bond. So that's what happens with the influence of the tide generating force from the sun and the moon. During spring tides, they become in phase. During mid tides, they become in quadrature, 90 degrees out. And they produce the minimum rate. Okay. Okay. So here we have the example that I was talking about. Also, we're going to So this is where we're going to go in late February. And there, the M2 is 0.41, the N2 is 0.09, the O1 is 0.06, the S2 is 0.06, and the K1 is 0.08. Notice that the N2 is greater than the S2. Right? So what that does is it produces a tidal modulation like that for the entire month. This for February of last year. So you can see that this spring tide has a much larger range than this spring tide, and this nip tide has a smaller range than that nip tide. So that's because of the influence of the N2. When you add an N2 to the S2 and the M2, you have this modulation that is asymmetric within one node. So I think I underscored this point last semester for those of you who took the class. If you are interested in spring tides and nip tides, you have to be careful where you are, because you might only get one good spring tide and one good nip tide in the entire month. So it's not every 2 weeks, it's only once a month that you get a good spring tide and a good nip tide. So if you're interested in sampling spring tides or nip tides, you have to be aware of this situation. Another example, so that again, this in Ponce de Leon has a form factor of 0.3, and that gets almost semi-diurnal between. Remember the cutoff was 0.25, so it's between mixed with semi-diurnal dominance and semi-diurnal. So that's why we see here during nip tides we see a strong asymmetry between the consecutive lows. So that complicates things. The other place where we're going, in Panama City, you have those values. Notice the values are much smaller. So, and the form factor. So given those values of the constituents and the form factor, what can you say about the type? What are you expecting? Yeah, diurnal, right? It's greater than 3, the form factor. And for the month of February, those are the tidal prediction. So you can clearly see that. What can you clearly see there? How many cycles per day? So the 1 cycle per day. During nip tides, you might get something funky here. Maybe become semi-diurnal just 1 day out of 2 days out of the month. You get semi-diurnal current. But other than that, it's diurnal. Supposedly we're going to be sampling on this day 13 and 14. So that's getting closer to springtime. Okay. All right, so let's talk about co-oscillation, which is what happens in estuaries. Estuaries co-oscillate with the ocean. How much of a tide do you have in an estuary? So if you were to close off an estuary at the mouth, what would the tide be in there? It would become practically a lake. Right? So the tides would be tiny. So the tides that you see in estuaries are really the co-oscillation of the estuary with the ocean. So it's the oceanic tide that comes into the estuary. So the independent tide in estuaries would be rather small. The co-oscillating tide is really what we observe in estuaries. So as the wave propagates into the basin, it can be modified in 2 ways. It can produce resonance, that is, it can amplify, or it can be rectified That is through, just like a wind wave gets rectified as it gets to the braking area. Because of nonlinear effects, it gets distorted. That's what we're calling rectification. The wind wave gets distorted. Like you guys who surf know that the waves that you surf are not nice and sinusoidal. They're peaky. So those are rectified waves. Those are not open ocean waves. And that's what happens to tides also. When they get to shallow waters, they get rectified. They become peaky or distorted. And that's what we're calling rectification. They get rectified or modified. So we'll see what happens as the tidal wave propagates into the estuary. All right. So let's first assume a wave that's linear, frictionless in the x direction and under homogeneous conditions. You can apply this also to wind waves, that the accelerations are produced by the slope of the sea surface elevation, nothing else. And the momentum with the continuity equation integrated vertically can be given as that. That's a continuity equation in one dimension, which the divergences are provided by the rate of change of surface elevation. So with those two equations, with two unknowns for u and eta, we can solve. And the solution for that system of equations is that wave equation. It's a simple wave with a phase that depends on distance and time. This is the amplitude of the wave. So we're calling kappa the wave number, 2 pi over the wavelength, and sigma is the frequency of the wave, 2 pi over the period of the wave. You've seen this. This applies to wind waves. So the wave looks something like that, simple. And this is for the case of a wave at one point, changing the level changing over time. So with this solution, we can use this solution to obtain the value for the flow for u, the tidal flow. So first, we use d eta dt 1 over h minus 1 over h d eta dt equals the differential of eta with respect to time is the cosine. Right? The differential of sine is cosine, and then we have minus sigma cosine. So that's why you don't have a minus anymore here, and you have the sigma cosine out of here. So that's du dx. So what do you do then to obtain u? Integrate with respect to x. So then you have a factor that's 1 over kappa. The integral of cosine is sine. So you have sigma over kappa of sine kappa x minus sigma t, and sigma over kappa, that is the frequency over the wave number, is the same as the wavelength over period, or the phase speed which is c, which is the phase speed of the wave. So we have c over h, phase sine. So that's how this is a very nice result, because you can use it as a zero order approximation of what kind of currents you would expect from a tidal amplitude, from eta. So knowing eta, you can calculate u from this expression. See that? So there's the wave. Yeah, I'm not going to switch to the other projector because it's just a plane wave that changes in time and in distance x. So this is a laboratory, as if we had gone to the coastal lab, filled up one of the tanks with water, and then generated waves. Is what you'd see. And that's eta equals amplitude times sine of kappa x minus sigma t. So that's what we have. The relationship between surface elevation and current is given like that, in such a way that the ratio of surface elevation to current is water depth over the phase speed of the. So for the case of the tides, of tidal waves, this c equals what? Square root of dA. See, I told you, it comes back several times. So if you see that both eta and u have a sign of kappa x minus sigma t, so this indicates that the flow is in phase with the elevation. For progressive wave, the flow and the particle velocities are in phase. You knew that, but you've seen that many times. So it means that eta and u are in phase. So the maximum current occurs at high water or low water, and zero current at equilibrium level. That's what it means. Well, this is the same thing, the wave at different locations, so I'm not going to go through. So now, for a standing wave, we have the same momentum balance, the same continuity equation. But now for a standing wave, we have two waves traveling in opposite directions. So the solution is a wave traveling in one direction and this wave traveling in opposite direction. So a sum of signs will give us this identity. So that's, for a standing wave, eta equals that. And then we can follow the same arguments as before and differentiate this eta with respect to time. So we get the sigma cosine. So that's what we have here, cosine and sigma. And then we integrate with respect to x to get the u. And again, we have sigma over kappa. So we have the flow, the tidal flow, or the wave particle velocity in general, equals the phase speed of the wave divided by the depth times the amplitude of the wave, cosine, sine. So notice now what happens to the phase. We have cosine of kappa x here, we have sine of kappa x. We have sine of sigma t, we have cosine of sigma t. What does that mean? That they're 90 degrees out of phase. So I don't know if, let's see. Can we go to the coastal lash? Generate a standing wave, and we idealize it a little bit in the sense that the incident and reflected waves are drawn as meshes, and the sum of the two are given by the colored surface. So try to look at the colored surface first. And that's the standing wave. We have two standing waves, two full standing waves. And then, if you can see two meshes, I don't know if you can see the distinguished two meshes. The lightly colored one propagating in one direction, and then the darker mesh propagating in the other direction. So the summation of the two of them is what produces the surface envelope. That's two times. So again, what I pointed out before, that we have cosine kappa x for the elevation, but sine of kappa x for the flow, sine of sigma t for the elevation, cosine of sigma t. So this indicates that the flow is out of phase with the elevation by 90 degrees, which means that the maximum currents appear at the equilibrium points of the elevation. And so these standing waves can produce resonance, and we'll talk about the requirements for resonance in a basin. So when we're done with this, we'll take a break. So in order to have resonance in a basin that's closed in one end but open at the other, what we need is that at the mouth we can have a wave, an incident wave, that we're going to call A naught, sine of sigma t. And this is the general expression for the standing wave. So for there to be a standing wave, if we substitute these into that, we have that. That is, if we substitute this into here, at the mouth, what we get is that A cosine kappa L sine sigma t, because we say that at x equals L, so we have substitute this x and put the L. That's going to be equal to eta, which is A naught sine of sigma t. So we have sine of sigma t that go away. So the amplitude of the standing wave at x equals L has to be A naught cosine of kappa L. So in general, the standing wave would look something like this. So the requirement for a standing wave is that the denominator equals what? So in other words, for there to be resonance, eta has to grow to infinity. So the requirement for eta to grow to infinity is that the denominator goes to. So what do we need for the denominator to go to zero? That cosine kappa L goes to zero. So that kappa L equals 90 degrees, pi over 2, or any multiple of pi over 2. So for resonance to exist, the denominator should tend to 0. That is, kappa times L should be equal to minus pi over 2 plus any multiple of that pi over 2. So from this, you can see that 2 pi L equals minus pi over 2 plus 2n pi over 2. So we have 2 pi over lambda, where L is the length of the system, lambda is the wavelength, equals pi over 2. When we factor this out, we have 2n minus 1. So notice that we have pi on both sides. So what we have is that the length of the basin has to be 1/4 of the length of the wave for resonance to exist. And we'll have different modes of oscillation. N it can be 0, or it can be 1, or 2, or 3, or can be. Actually, we should start from 1. Actually, when n equals 1, we have the basic mode of oscillation of the system, and it's a quarter wave. That's what we call quarter wave oscillation. That we have 1/4 of a wave, of a standing wave, oscillating in the basin. Notice that the basin is closed at the head and open at the mouth. When we have a lake that's closed at both ends, what kind of oscillator do we have? Quarter wave oscillator, or it would be a half wave oscillator for the case of a lake. Okay, so since lambda equals the phase speed times the period of the wave, we can determine the natural period of oscillation, which is 4 times the length of the basin divided by the square root of GH. So this natural period of oscillation is the period at which we should force a system to have it resonate. So you have your bathtub, you can do this experiment in your bathtub. You can actually do it in your bathtub. But that would be a half wave oscillator. Instead of having 4L over C, you're going to have 2L over C. And C, how do you determine C? Square root of GH. So you have to measure how much water you put in there, or how deep it is. So 2 times L, you have to measure your bathtub. So that will give you at what frequency you have to force the water in the tub to make it resonate and maybe spill over there, depending on how much water you put on. So that's a requirement. Probably you've heard about this example in many other places. But in the case of a semi-enclosed body of water, it's 4 times the length of the system divided by the square root of GH. And you'll have different modes of oscillation depending on whether n equals 1 or greater. All right, so we have the natural period of oscillation is that. If you force a basin, a semi-enclosed basin with that period, then the amplitude will be given by that of the oscillation, and the current will be given by that. Notice also that the phase is 90 degrees out of phase. So where eta is maximum at the head of the basin, the flow is 0, and where eta is 0, that is at the node of the standing wave, the flow is maximum. That's at lambda over 4. And you can put the numbers in there, and you'll see that when at x equals lambda over 4, eta is going to be 0, and u is going to be maximum. So I'm not connected to the to the network here, but we'll look at an example of station, a beautiful example of station, something that helps me understand the concept. See if we can connect to this. So right click on that example of station. Basically, this web page that you'll see a quarter wave resonator. And you see the little board? And you see the little particles at the head of the mouth? And now you can see it. So you can see the surface elevation, they're going up and down. You see the node at the mouth of the basin. And the maximum eta at the head of the basin. And you can see that the excursions, that is the U is maximum at the mouth, and is 0 at the head. But at the head you have maximum displacement of the vertical motion too. Right, so that's the nature of a sage, a standing wave, first order sage. Right? So you can see that for an estuary with length 1/4 of the wavelength, U is 0 at the head and maximum at the mouth. That's what I said already. And for longer estuaries, U is 0 at the head, x equals 0, at lambda over 2, and at 3 lambda over 2, etc., where sine of kappa x equals 0. And the flow is maximum at lambda over 4, 3 lambda over 4, 5 lambda over 4, where sine of kappa x is maximum. That is where this is maximum or 0. Okay, so some examples about station. We have 3 examples here. Long Island Sound, which is in the northeastern coast of the U.S. This is Long Island Sound. It has a depth of 20 meters, so you can calculate the phase speed, square root of GH. The length is 180 kilometers. The square root of GH is 14, and you can calculate the mode 1 of the natural period of oscillation is 14 hours. Chesapeake Bay gives us a natural period of oscillation of 28 hours. And the Bay of Fundy gives us a natural period of oscillation close to 11. So out of these 3 examples, where would you expect saging or resonance from the tidal forcing? From the 12-hour tidal forcing? Where would you expect resonance? Where? Bay of Fundy, indeed, that's the largest tides on the Earth. That's close to its natural period of oscillation is close to the forcing period. And also in Long Island Sound, you have resonance in 3/4 of the basin, up to where lambda over 4, up to lambda over 4, you have a standing wave that resonates. Chesapeake Bay, there's no resonance of it for the tidal period because it's far from the forcing period. Okay, so let's take a 5-minute break. Come back.
I have a question. What? What's the difference between centrifugal